students, welcome back. This is Torres, Elbow Bump. How are you? Are you doing okay? Is your family okay? Remember, if you need anything, please send me an email so that I can help in some way or another. So lucky you, you get to hear my voice for another lecture. But the best part is we will continue our work with the normal curve and we'll start to talk about Z-scores. Yay! So this photo or this image is a copy of the normal distribution, okay? As you can see, it's unimodal, okay, has one mode in the center. The mean and the median are probably really close to one another because that is a symmetrical curve. The tails are of equal length. It looks good. It's got the shape that the normal curve should have. Now, if you have a normal distribution, and only if you have a normal distribution, the following will always happen. This is a given. This will always happen, okay? Approximately 68% of your values will exist within one standard deviation before and after the mean. So that's meaning this information right here. So let me try to write on this. Where's my pencil? There it is. Okay, I'm going to try to make this in pink. So right here, what I'm coloring right here, this is 68% of all the values. So just think of it as if I had 100 values. If my distribution is normal, then approximately 68 of those values would exist within one standard deviation before and after the mean. If and only if I have a normal distribution, then I will always have approximately 95% of all my values exist within two standard deviations before and after the mean. So if I color this in, I'm trying my best to, ugh, that's ugly. Okay, about 95% of all my values will exist within two standard deviations before and after the mean. Okay, if and only if I have a normal distribution, then approximately 95% of my values will exist three standard deviations before and after the mean. So all of this will include, and this will include this little tiny sliver in through there, and all this kind of, and all this in between. Okay, so as you can see, the further I get away from the mean, I will incorporate more of the values. Okay, so think of it this way. If I had, say for example, I had 100 pennies, okay, and if you ever looked really close on a penny, you would see that every penny has a year on it. If I took all those years and I figured out what the average year was, and I figured out the standard deviation for the years for all those pennies, then I would have approximately 68% of those pennies would be between one standard deviation before and after the mean. 95% or 95 of those pennies would be between two standard deviations before and after the mean. And about 99, all but like one penny, would exist within three standard deviations before and after the mean. Okay, so what does this mean? Well, funny, I should put it that way. Everything is most likely to exist in the center region. The closer you are to, and I'm going to try this one right here, this tool. The closer I am to the center right here, that's where most of my values will fall, very close to the mean. The farther I get away from it, there's less of a chance of that occurring, but more of the mean is taken up. So let's look at this a little bit more detail so we can just really make sure that we understand where these numbers are coming from. So I'm going to talk about this first little piece right here. This is 68% of the curve, and notice that what they did is they went ahead and divided it into two pieces that I'm just going to kind of, this time I'm going to try to color nicely. Here is half of the 68, which is 34%, and half of the 68, which is 34%. We've got 34% plus 34% makes up that 68%. Okay? And if we add a little bit more as we get away from the normal curve, we've got this little section right here, and we've got this little section right here. And together we have 95%, right? So we have 95%. We're going to subtract the 68% that we already accounted for. Basically what we're doing is we're subtracting this pink, and we're going to end up with 27%. 27%. And if we divide that in half, we're going to find that each of those halves comes out to 13.5%. Okay, so far so good. Then we know that if we add this little piece out here, this little red piece, and this little, oops, I keep pressing these buttons, this little red piece, we've got an additional 4%, right? So if we've already taken up 95% of the curve, and all that out here and out here ends up being 99% minus 95%, that's 4%. And if we're going to divide that by 2, that gives us 2% on either side of the standard deviation. And then when we have 1%, that kind of is left out on the sides. Okay? So if you think of this as probability or the chance occurrence of something happening, you would have a 68% chance of things happening within one standard deviation before and after the curve. Okay? You would have 95% chance of things occurring within 2 standard deviations before and after the curve, and 99% chance of things happening 3 standard deviations before and after the curve, and anything else than that, there would only be a 1% chance of that occurrence. Now, just like we can discuss the standard deviation or these percentages kind of working from the center out, you can also look at them as you go from left to right. So I'm going to go ahead and bring over another blank curve. This one's just blank. Okay, and I'm going to go ahead and try to make that a little bit bigger. Come on, guy. Yes. All right, and I'm going to just kind of scooch this up. Look how much better I'm doing. Okay, this is good. Okay, and then let's talk about what's happening here. Now, this is going to be, we're going to call these our Z-scores right here. These are our Z-scores. I like to refer to them as anchor Z-scores because they're the ones that we talk about like as a whole Z-score. So here, our Z-score that would be equivalent to the mean would be the 0 Z-score because that's kind of like the center. If we were looking at one standard deviation above the mean, it's going in the positive direction, so we'd say it's a positive 1 Z-score. And this distance right here would be the standard deviation. Now you can see standard deviation abbreviated, I can never say that word, different ways. If you're talking about the population standard deviation, you would see it as like a sigma. If you were looking at a sample standard deviation, you'd see it as an S, but a lot of times in literature, we just see it as SD. So I've gotten into the kind of perhaps bad habit of using SD, but I do want to make sure that you're aware that there can be other types of notation. So this is the standard deviation. I'll just put standard dev for population. That would describe, it's a population parameter. This would be a standard deviation for a sample. So it would be a statistic. And this is just shorthand for standard deviation. Just SD, standard deviation. Okay, so here's one standard deviation above the mean. It's going in the positive direction. This is also going to be another standard deviation right in through here. This is going to be another standard deviation and through here. And standard deviations can just keep going indefinitely. You could have something that is 15 standard deviations above the mean. That would signify is that it's a very rare occurrence, because as something becomes much greater than the mean or much lower than the mean, then it's not where most of the values are expected to exist. So here I'm at 1 standard deviation above the mean, so this anchor Z-score would be positive 1. 2 standard deviations above the mean, this anchor Z-score would be positive 2. 3 standard deviations above the mean, this anchor Z-score would be positive 3. The same happens in the reverse. So if we were going to look at what happens below the mean, okay, these areas are still standard deviations, and so because it's below the mean, this is going to be 1 standard deviation below the mean. This is another one, 2 standard deviations below the mean, so this would be negative 2, 3 standard deviations below the mean, and this would be negative 3. Now, again, these can keep going. When we start looking at comparing a statistic next to another statistic or next to a parameter, then you'll see that things can really be much greater, much lower than 3. Okay, so this is what I like to call just the anchor z-scores. We just use them often for reference. The nice thing about the z-scores, it's a standardized measure. So regardless of what you're working with, whether you're working on salaries and the mean of a salary and the standard deviation of a salary, if you're working with how much air might go into a tire, if you were looking at scores on exams, things like that, regardless of what unit you're discussing in your statistical analysis, you might not know if the mean of something like that, what the purpose of it is. Like, I don't know what the average pounds per square inch of a tire should be. But if somebody says, you know what, the pounds per square inch for that tire right there is 2 standard deviations above the mean, I would be like, wow, that thing's getting ready to explode, right? Because it's much, much greater than what it's supposed to be. So the z-scores are a standardized way of discussing measurements that you can use regardless of what you're measuring. Now, if we were looking at, if we were going to talk about corresponding raw scores, oh, that is an ugly line. Okay, here is a raw score equivalent. So then you'd have to know exactly what is the mean and what is the standard deviation for that particular situation. So I'm going to work with one that I often work with, which is the IQ test information. So the IQ test is a measure of the capacity for learning, and the mean of the IQ test, I'm going to write it as X bar, is 100. Standard deviation is 15. So if I'm looking, and it's a normal curve. It's a norm reference test. So if I'm looking at this particular situation, I can say, okay, well, I know the IQ test is a norm reference test, and it's got a mean of 100. So the 100 is going to go right here in the center. And this distance right here is 15. This distance right here is 15. This distance from here is 15. Same is happening over here because it's a standard deviation. It's the same throughout the curve. Doesn't change. Increments that are the same, equal intervals. So let's see what happens. So if I have a score that is 1 standard deviation above the mean, and my mean is 100 and the deviation is 15, then I know that my corresponding raw score for a z-score of +1 is 115. If I were continuing to go in the positive direction, another deviation higher than that, then 2 standard deviations above the mean would have a corresponding raw score of 130. 3 standard deviations above the mean, if the mean is 100 and the standard deviation is 15, the corresponding raw score would be 145. Now in the opposite direction, the same thing is happening. Basically, we're going to start subtracting because we're going in the opposite direction. So here is 100. What is a corresponding raw score for 1 standard deviation below the mean? When the mean is 100 and the standard deviation is 15, then that's going to be, it's going to be 85. 2 standard deviations below the mean, the corresponding raw score for a z-score of -2, when the mean is 100 and the standard deviation is 15, would be 70. And if I wanted to go another standard deviation below that, then the corresponding raw score for a z-score of -3, when the mean is 100 and the standard deviation is 15, then it would be 55. Just when I thought I was rocking and rolling. Okay, here we go, 55. Yay. Okay, I did it. Now this is for the IQ test. So let me just write IQ test over here. Now let's think of another type of test that is a norm reference test. Another popular norm reference test is the SAT test. SAT exam. Okay. Many people take the SAT exam right before they go into college. You might have taken it, maybe not. But the purpose of the SAT exam is it's a predictor of a person's success in their first year of college. It's one of the predictors that they use. So the SAT is a norm reference test, meaning that the scores are normally distributed. They have this pattern. For the SAT exam, the mean is 500 and the standard deviation is 100. Perfect. All right. So I can still use this right here, right? What's going to change? Well, what's going to change is the raw scores. The Z-scores are going to stay the same. They don't move. They're standardized. They're fixed in place. However, depending on what type of test and what the mean and the standard deviation is for that test, these raw score equivalents will change, as would the width of this. So instead of it being 100 in the center, 500 is in the center, and these are now no longer 15, but they're 100. So now I know that my mean is 100. If I wanted the corresponding raw score for the SAT exam that was one standard deviation above the mean, then I know that the corresponding raw score would be 600. The corresponding raw score for a Z-score of positive 2 for the SAT exam would be 700. Okay, now listen to my question and see if you get an idea of how this would go. All right, so I'm going to mix it up a little bit. I'm going to say, what is the corresponding raw score for a Z-score of -2 on the SAT exam? You can do this a couple ways. You can keep filling out the raw scores so you have an idea of where things fall, or maybe you can do this in your head. If you want to give yourself a couple seconds to pause the video and see if you can do it on your own, then you're welcome to. I'm going, just for the sake of time and with the understanding that you guys can pause this whenever you like, I'm going to go ahead and just fill everything in. So I'm just going to keep going over here for 800, and I'm going to come over here for 400, 300, and 200. And then I know that the corresponding raw score equivalent for a Z-score of -2 is going to be 300. 300 is the raw score equivalent for a -2 Z-score. I promise to get better with my handwriting too. I'm really trying. I don't know if you can tell or not, but I'm really trying. Let's just do another one really quickly. I'm going to go ahead and put this blank curve over here. Make this a little bit bigger. And I'm going to say, I'm going to make it up. I'm going to say that my students, that I gave a quiz. I'm not going to even tell you how many questions were on the quiz, but I can tell you that on average, most students receive 37 points on the quiz. Now, don't freak out. That doesn't necessarily mean that it's a low score, because you don't know how many points were possible. Maybe 38 points were possible, and that's a really great score. And maybe 50 points were possible, and that's not such a great score, or 100, and that's a really bad score. So the point is that you're not sure. And I'm going to say that the standard deviation for my exam is 2 points. Take a second, and I know this just goes up to +1, +2, -1, -2. Go ahead and draw those in and see if you can figure out what the corresponding raw score equivalents are for all the standard deviations on here. So let's fill this out. This is going to be 37. This distance is going to be 2. It's going to be 2. It's going to be 2. So this is going to be 39, 41. And if I kept going to 3, this would be 43. Opposite is happening in this direction. This is going to be 35, 33. And if I kept going, it would be 231. Okay, so you would be able to find the corresponding z-scores. Now, let's take this 41, for example. One way, if I wanted the raw score equivalent, and we're gonna call these z's, and we're gonna call these x's. So what I could say in this situation is, let's just say that I want to know what the corresponding z-score is for 2 standard deviations above the mean. And I figured out it was 41, right? So let's just see what would happen if I took 41 and I subtracted the mean and I divided it by the standard deviation, which is 2. What would I get? Well, here I have 41 minus 37. That's going to be 4 divided by the standard deviation, and I get positive 2, which is that. Let's see if it works the other way around. If I have, let's just say I have this one, 35. 35 minus the mean divided by 2. Well, I've got 35 minus 37, so I'm going to end up with negative 2 divided by 2, and I'm going to get negative 1, which matches here. Okay? And really what this is it's the z-score formula. So I can find a z-score by using the raw score that I want, which is x, subtract the mean, which is x bar, and divide it by the standard deviation, and that will give me the z-score. Let's try one just so I can kind of show you how it works. So let's try this one that we haven't tried yet, 43. Now 43 is going to be positive, right? Positive 3 is what we're looking for. So 43, we're going to put here, that's x, minus the mean, which is 37, divided by the standard deviation, which is 2. So I have 43 minus 37, that's 6, divided by 2 is 3. Can you see that all the way over there? Let's see if I can move this over a little bit. Right over here. So it worked out. It was 3. I'll write that a little bit better. Boop. Okay, which is 3. Right, so it works out really nicely that if you have the raw score and you want to know what the z-score is, you can just use the z-score formula and plug it in, but honestly it works just as well if you want to draw it out. You have to decide at this point what makes sense to you. If something doesn't make sense to you, then why use it? So what's the big idea? Today's big idea is that if the distribution is normal, the probability under the normal curve remains fixed. The area under the curve describes the probability, and this area can be coarsely segmented by anchor z-scores. The other big idea is that z-scores describe values relative to the mean in a standardized way. Positive z-scores describe values that are above the mean, and negative z-scores describe values below the mean. So that's it for today. With that said, don't forget to check your emails, check Blackboard, do your homework, and subscribe to this channel. Even better, hit that notification bell so you know when there are new videos for this course. Okay, this is your teacher Torres saying stay safe, and I will be waiting to give you a virtual elbow bump in the next video. Ciao!